Okay, it's 4 o'clock and we're ready to start. Good afternoon, everyone. Welcome to the first ECE Distinguished Colloquium of Spring 2021. It is my pleasure to introduce our distinguished colloquium speaker today, Professor Athol Campbell, from our own astronomy department, who is also a Blue Waters professor here at Illinois, and also affiliated with the National Center for Supercomputing Applications. Professor Campbell is an internationally recognized scholar in high-performance computational astrophysics, with seminal contributions to some of the most fascinating and fundamental research questions in observational astrophysics. He's a pioneer in the transformative change that we're witnessing in the practice of observational astronomy, caused by the exponential growth of advanced computing capabilities, with contributions in a wide range of areas spanning the theory of interferometry and interferometric imaging, astrophysical masers, stellar evolution, and gravitational lensing. Professor Campbell has also been instrumental in the development of some of the most awe-inspiring observational capabilities in astrophysics. For example, the Vera Rubin Observatory, that is also known as the Large Synoptic Survey Telescope, and the Square Kilometer Array. Just to give you a sense of what the magnitude we're talking about, the Vera Rubin Observatory has an 8.4 meter primary mirror and a 3.2 gigapixel CCD imaging camera, the largest digital camera ever constructed. The Square Kilometer Array is an intergovernmental radio telescope project being planned to have a total collecting area that will make it 50 times more sensitive than any other radio instrument. It will require very high performance central computing engines and long haul links with a capacity comparable to the global internet traffic. It is conceived to survey the sky more than 10,000 times faster than before. So I should mention that in addition to his distinguished scholarship, Professor Campbell has been frequently named in the list of teachers ranked as excellent. So you can be sure that we are in for a treat this afternoon. Please join me in welcoming Professor Campbell.
Well, thank you, Farzad, for a very generous introduction. It's an honor to be invited to speak to you, and my collaborations and friendships with ECE members in my time at UIUC has been a real highlight of my time at the university. So today I'm going to talk about a project I am working on with a, I need someone to enable screen sharing, sorry. Try that out there. Is it enabled? So it's a project I'm working on with Michael Katolik, who's shown on the slide, a graduate student in astronomy. And I'm going to discuss some areas we've been exploring, new algorithms in phase calibration and imaging and interferometry that have some very compelling science and technical drivers at the moment. So this is a dangerous slide. What are these science drivers in contemporary astrophysics? The big problem that we really face in modern cosmology, the study of the evolution of the universe and the history of the universe, is that we don't understand a very large fraction, 95 or 96% of the matter energy density in the universe. So in this Big Bang picture that's shown here, where the universe has been evolving for 13, 14 billion years, we don't understand what is driving recent acceleration, dark energy. We don't understand the nature of dark matter, which interacts with gravity but does not radiate. And we don't have a full understanding of galaxy evolution throughout this period, from the Big Bang to when the first stars formed, known as reionization, through to the present. And coupled to this is uncertainty about whether our current theory of gravity, general relativity, is correct. So this is a large error for astrophysics, but it would be a catastrophic error in engineering. And so these are really profound challenges in the field right now. And to study them, it's driving us into what might be called the Great Survey era, where we have to sample the universe over very large cosmic volumes of solid angle and redshift, where redshift is the distance back to the Big Bang, cosmological shifting of emission, and ideally with very fine time sampling, because the latter allows us to study very compact relativistic objects like black holes and their environments. And so this is a dramatic change for astronomy. For many years, it was more targeted field looking at isolated objects of interest. So coupled with these science drivers are being enabled by very profound engineering advances. This is perhaps the most unnecessary slide to ever show to an ECE department, but Moore's law is driving the number of receptors and detectors you can use in observational astronomy. It's driving the software-hardware boundary far closer to the receptors than it used to be because of advances, say, in analog to digital conversion. And the computing and networks are allowing very high throughput survey operations. So there's a coupling between these profound science drivers and very important engineering advances. This is the Moore's law of optical astronomy, which is considerably less impressive. This shows the aperture size of optical telescopes going back to the time of Galileo. And you can see that the doubling time there is about 40 or 50 years. So the difference between those two timescales are producing a profound and disruptive change. We exploit the engineering advances, but they in turn produce very challenging problems for us to address, both in digital signal processing and in the data handling. So what are two canonical telescopes from this era? I chose two that I've been involved with as far as I've mentioned. So the first is the Vera Rubin Observatory, which will produce a legacy survey of space and time known as LSST. This is a photometric telescope, it's not spectroscopic, and will survey billions of galaxies to measure those imprints, primarily of dark energy, and also to understand the deflection of light from those very large distribution of galaxies, which is another way through gravitational lensing that we can discern the nature of these unknown constituents of the universe. It'll observe the sky with a 10 square degree instantaneous field of view, which is very large, every few days, and therefore also open up the transient optical sky for the reasons that I mentioned earlier. So you can see these engineering trends here very dominantly. The camera is 3.2 billion pixels shown at lower right. It'll produce 15 terabytes of data a night, and an archive that's hundreds of petabytes in final size. So a very different type of astronomy. The radio counterpart is the so-called Square Kilometer Array that Farzad also mentioned. The Square Kilometer refers to the target collecting area, and its aim has many overlapping science goals with the VRO and LSST. It's going to map the position of galaxies from their neutral hydrogen emission, which is a hyperfine transition at about 1420 megahertz. So very manageable with radio technologies. It'll also study the transient sky, particularly curious objects like pulsars around black holes that will allow us to test general relativity. And the engineering wave it is riding is it will use semi-commoditized antennas somewhere between satellite dishes and custom engineered parabolas for cost, very high-speed network, signal transmission, image formation will require HPC, and the digitization will be very close to the receptors, much closer than traditionally was the case, and also making use of FPGAs, GPUs, instead of ASICs, for example, which were very common in these types of previous instruments. So the SKA will make very profound demands on our capacity to form interferometric images, and I'm going to narrow down and talk about a specific problem in that area today. So I'll narrow the concerns to that because that's the primary topic I'd like to cover. So in this era, in radio interferometry, especially at a survey level, the thermal sensitivity of this array is, here it's assumed to diminish by root n as the number of baselines. And I should just point out that that term SEFD is the system equivalent flux density, the system temperature of each antenna expressed in Janskis, where Janskis are shown at the lower left for someone not familiar. Jansky was a very famous radio engineer who couldn't remove an irreducible sky background and accidentally started radio astronomy. So you can see that the requirement for fidelity of the imaging, here expressed as a simple proxy of dynamic range, is very profound, 10 million or more to 1. And the community practice, which is highly customized, struggles to address that. So if we summarize the challenges more broadly, and then I'll describe the problem I'll discuss, is that our data model for the interferometer is becoming more complicated. The sensitivity requires that we correct systematic errors at a commensurate level. Signal to noise frontier is usually the science frontier, and we have to have a much better understanding of the fidelity of our images for reasons I'll describe in a moment, and the calibration fidelity. And also the engineering advances are fantastic for enabling these instruments, but they make the problems into high performance computing problems for the data management. So I'll provide a very brief overview of the theory of interferometric image formation, not in any great depth, just to set the context for the algorithm I'd like to talk about today. So a modern expression of this is this data model shown here. Its primary modern advantage is that it uses Jones matrices from optics to capture the signal path at each antenna. So in interferometry, as you'll be aware, there's two fundamental planes. The plane in which the spatial coherences of the radiation are measured, known in this field as the visibility plane. And this integral equation connects it to the source brightness distribution, which is that symbol S on the right-hand side. And the Jones matrices, the calibration of propagation effects, may be direction dependent or not direction dependent. Radio interferometry is greatly benefited by the availability of heterodyne down conversion, up to frequencies below, say, 1.5 terahertz. So these spatial coherences can be formed after detection, which is of course not possible in optical interferometry. So asymptotically, this integral equation becomes the Transitive-Zernike theorem, where the spatial visibilities Fourier transform to the image plane. So this just shows the signal path and the direction of the forward and inverse problems. So image formation in interferometry is an indirect inverse imaging problem, and it's a highly coupled data model. Generally, the source structure is not known, and neither are the calibration terms along that path. Here I've shown a Jones matrix just as a refresher of the format. The primary advantage they offer is that they allow the signal transfer to be expressed in a modern optical form, but also they allow arbitrary polarization bases. So you can either have circularly polarized feed or, say, linearly polarized feed. The types of errors that affect interferometers are there's phase noise from phase decorrelation in the atmosphere. You can see the incident wave in the top right figure is corrupted by propagation through the atmosphere. And the lower left figure shows a typical characteristic Kolmogorov turbulence pattern. The contribution to the error differs between optical astronomy and radio astronomy. In optical astronomy, it's primarily temperature fluctuations changing the refractive index. And the length scale is characteristically 10 centimeters, the feed length, and the time in which you have to correct the phase is milliseconds. In the millimeter, as shown in the lower right, the forms of optical depth are indicated. Here, the time scale is more of the order of several seconds or a little bit higher. And the constituents are either water vapor, you can see, or lines like oxygen and other trace elements in the atmosphere. So highly variable. This figure on the lower right shows the optical depth at the VLA site. More on that in a moment. So fundamentally, why fidelity is a real concern, especially at this level of sensitivity, is that these arrays were able to advance very rapidly in the mid-20th century and beyond because of the technologies inherited in radio engineering. However, they are sparse apertures. The image reconstruction method led to a Nobel Prize by Ryle and Jewish in '74, but it's fundamentally an ill-posed image formation problem. This sampling of the aperture is shown at right. For an intercontinental type array at the top right, for the very large array in New Mexico, where I also worked previously, it's that image on the mid-right. So the UV sampling is not very good. Now, there's a close historical tie to the department. George Swenson, who sadly passed away in 2017, was a member of the team that put the VLA together. There was, in fact, a competing proposal from Illinois, but ultimately it merged with the National Center. But in this text from a memo he wrote in 1977, you can see what the state of the art was in imaging at that time. Essentially a direct Fourier transform of the spatial coherences into the image plane. There was very rudimentary calibration and no correction for the PSF, so no deconvolution. And the PSF can have quite high side lobes with that type of sampling. The computing section of the formal construction proposal is kind of interesting. It asks for the impressive quantity of 2 megaflops of computing. So at that stage, that was quite challenging. And today also, and this is my subject in many ways, we can take new approaches to this problem by exploiting HPC. So a very important tie, and George, of course, made major contributions to this. So at the time the VLA came online in the early 1980s, in fact, there was a very significant algorithmic development known as self-calibration in the field, which was not anticipated in construction. And here it's shown in a simplified form. If you consider the signal at 2 antennas, say E1, E2, some electric field converted to voltage by the antenna, and it has an amplitude and a phase error. These were very problematic in the design phase. It was realized pretty early on that an iterative solution that solved for the antenna phases and gains using a chi-squared minimization in the visibility plane, and then iteratively producing an image would converge with a regularization. So the effect of the minimal calibration is top right, adding deconvolution to remove the PSF is mid right, and self-calibration, meaning deriving gain corrections from the source, is the lower right. So it was a substantial advance. But there are uncertainties with this method that continue to produce challenges in the field for reasons I'll describe shortly. The self-calibration primarily works because of a quantity. There are closures around arrays of antennas in the interferometer, specifically the instrumental errors, which are denoted here by the deltas, cancel out in a sum around 3 antennas. And this is effectively equivalent to thinking about the antenna-based corrections, instrumental or from the atmosphere, as being antenna-based. And this was discovered in 1958 in this particular field, and then rediscovered a few decades later at the time the VLA came online. So this iterative approach, the very earliest self-calibration, moves between the 2 planes. It solves for the antenna gains. You have to have some model of the source to do that. And then once the gains are corrected imperfectly, an image is derived with deconvolution, and this is proceeded iteratively. But it absolutely requires regularization to converge because of the mathematical condition of the problem. And a whole variety of best practices developed in the field around how to steer this iterative process. And it works best if there's information balance between both planes. And this degree of best practice and heuristic regularization makes fidelity a continuing grand challenge in interferometry. So why does it ever converge? Well, if you look at the relative information provided by the closure triangle and the closure amplitude for antenna combinations, it does become a good fraction of the available measured visibilities as you increase the number of antennas. So this is still a significant problem in the field. If I were to summarize all the, the modern perspective of what the estimation problem is, the calibration problem is forming chi-squared somewhere in that data model. You can divide that product of Jones matrices G at any point where you're solving for a given term. And that's typically the visibility plane calibration for one of these Jones matrix components. And the image estimation is the update direction of chi-squared with respect to the source model. So given all these years that have elapsed, what's the sort of mapping of the current approaches that are used for self-calibration and imaging? Well, I've shown them here in broad categories. The absolute simplest approach is at the left, where a parameterized source model is used, say a sum of elliptical Gaussians. That's fitted in some maximum likelihood means to the visibility data, now very deprecated because of the sensitivity and complexity of the source. The classic iterative hybrid mapping I've described in the last few slides, alternating between a maximum likelihood estimation of the gains and phases, and then image formation and deconvolution, often with a simple deconvolution step like clean. A more contemporary version, but it does go back quite a while also, is regularized maximum likelihood estimation. That's the term that's unfortunately adopted here. It's also sometimes called forward imaging in this field, where the chi-squared is minimized with some side constraints. And the side constraints impose the regularization, like smoothness, compact support, positivity, for example. And an emergent area is full Bayesian estimation with priors. It's quite expensive in this field, typically map estimators. And again, it most frequently involves some assumption of a source parameterization. So all of these methods have implications for the uncertainty quantification or the fidelity of these images. So what I'll consider today, with having provided the scientific context and the technical background, is a new approach to calibration of antenna phases that I've called global stochastic calibration, that I've explored with Michael. This involves minimizing a functional of the reconstructed image, exploiting very large-scale ensemble imaging. And then I'll talk about modern approaches to fidelity assessment, possible also only with modern HPC. So what is this system that I'm proposing? It's inspired by an approach to adaptive optics in the optical. So here I'm considering incoherent, no phase optical imaging with a telescope. And of course, they need to correct the atmosphere on a very short time scale, milliseconds. The classical approach is in the left panel. The distorted incident wavefront enters the top left. A beam splitter feeds it to some form of wavefront sensor, perhaps a Shack-Hartman sensor that measures the curvature of the phase front. That is directly inverted into a set of corrections to something like what is used here as a spatial light modulator, but also deformable micro-machined mirror is also used. And that corrector will have a number of control channels that are indicated as U sub N. The more controls you have, the more sub-apertures you can correct, the more accuracy. In the mid-70s, a method was proposed by Muller and Buffington at Wright, which, with some input from Freeman Dyson, where instead of having a wavefront sensor and wavefront reconstruction, a functional was measured on the image, the quantity J shown here. And it's a derivative, say, of something like the Strel ratio, most typically. And this is model-free, the model-free approach. What you need is some form of optimization that then adjusts the phase of the incident wavefront until that functional is maximized. Now, of course, in incoherent optical imaging, they don't preserve these phases in the aperture. The quantum noise is too great to sample this. But in the radio, we do have these quantities. This method was also applied in synthetic aperture radar by Phenup in 2000. And his simulation is shown at the lower right, so the original image at top left. He then introduced some phase errors along the track, and he used a simple squared intensity functional as a sharpness metric. So the term sharpness function or objective function I'm using here interchangeably. And it's been used in radio astronomy in phasing up tide arrays, so not in imaging, but in combining an array as a single effective antenna, which requires correcting all the phases and then just summing the total output power. And that makes a good functional for this. So what instead we've explored is whether this algorithm can be used in the petascale era to do calibration, imaging, and interferometry. So we defined objective functions on the images motivated by physics and by sort of common community metrics of image quality in this domain. And then we used the particle swarm algorithm and very large scale ensemble imaging. So imaging hundreds of thousands of phase samples, phase distributions across the array, and explored the full calibration solution space, which is important to understanding fidelity. And this method doesn't require a source model assumption. It's less sensitive to optimization starting points, as in, say, Levenberg-Marquardt. It explores the full solution space, and it may have a lower bias because it doesn't have as many controls as that sort of fine-scale heuristic iterative method. So what do some of these objective functions look like that we've tried? We've looked at about 28. I didn't show them all in the interests of being kind. So these are just the families of the methods. Top left is shown the encircled energy inside, say, the point spread function main lobe, the PSF from the array. That's in the sort of broad encircled energy or Strel ratio type family. You can look at a different radius with a circular region shown in the center top. Dynamic range, the peak at the center of the image relative to the RMS in outer regions, those squares indicated. Lower left, that can also be done with annular regions. Another metric that's used in this field is looking for the deepest negative, which you can have in a poor image that's badly phase calibrated. And that's one of the heuristic regularizations used, so we incorporated that. And then another weak one, which is just the RMS in the outer region. I should mention that the image I've chosen here is badly phase calibrated, so it looks more interesting. So it's highly parallel decomposable, and the way this works is to generate what we explored is a random initial distribution of particles, population. Then at each particle position, we calibrate the data, make an image, compute the objective functions, and update the particle location here just using the Firefly algorithm. It's highly parallel, it's very feasible on a system like Blue Waters, petascale, and we use community codes in a common framework to do the underlying interferometric imaging. So the first thing we looked at was a random sampling of these 28 objective functions to see if they monotonically decrease against the known mean squared array and the antenna phases. Given that these are simulations, we know what the antenna phases should be. So I've shown this for the same objective functions here in the same positions. And I should bear in mind what we're doing here is we're projecting an 8-dimensional space for this particular simulation into this 1-dimensional crosscut. So it's not all that revealing. But encircled energy obviously monotonically decreases. We want things to go from the top left to the lower right. Dynamic range is not too bad, but others such as the deepest negative or the outer region RMS doesn't show strong discriminating power. At least it's not promising at this point. These are on images where there's no deconvolution applied. So it's the principal solution, only without the PSF removed. This is with deconvolution, and the only striking thing I'd mention is that some quantities like dynamic range, top right and lower left, become much more discriminating because the effect of phase errors is to distribute power to the side lobes, just generally speaking, and so that effect is suppressed. And the Strel family, or the encircled energy family, remain promising. The deepest negative and the alt-source RMS remain unpromising. So our next stage of research, I'm repeating the algorithm figure here, only I'm not going to go through this again, was to apply this stochastic optimization iteration to a variety of source models, dimensionality in the solution space, and with or without deconvolution to see how it converged. So the first slide I'm showing is a point source, so unresolved function. We're using the encircled energy in the PSF synthesized main lobe as the objective function, and there's no deconvolution. The x-axis is the known mean squared error in antenna phases in the array. We're not modifying amplitude at this point. And the iteration number is inset, and the color wedge shows the firefly particle density. So again, it's a location of particles in the 8-dimensional space, but projected here in 2D. But we do notice that there's pretty rapid convergence. We've adjusted the objective function so that the best value is the lowest value. So the solutions we want to find are the lower left of each of these panels. So it's quite rapidly convergent. There are regions of feasibility in the solution space, which is interesting. And once particles get stuck in these hard or impossible regions, they appear not to escape. This is an animation of that convergence, otherwise identical. So pretty rapid convergence, which is encouraging. The starting point image is quite poor. This color scale, the black regions are completely negative. And you can see there's a lot of power distributed all over the image in an unfortunate manner. In the final iteration, the best image is shown lower left. I should remind you this is a point source with no deconvolution, so this is pretty close. This is very close to. It's an excellent approximation to what we would hope to find. The PSF has not been removed, but as you go to these other regions, you can see that the images degrade rapidly. And this ties into our understanding of fidelity. If you look at image D, for example, there's clearly spurious symmetrization, which is the term used in this field, an artificial splitting of the source because of various biases in the solved phase. So this is quite encouraging, and clearly these regions indicate places where the phase solutions are stuck in some local minimum. Our next example is increasing the dimensionality by a factor of 10. So increasing the number of phase corrections across the array to of order 100 different quantities. And the convergence is again quite rapid, but the regions in the solution space multiply. And there's reasons we would expect that, as we'll discuss later. I'll animate the series of panels just to show that it again converges fairly quickly, not as fast as before, and shows highly segmented solution structure. This is for the higher dimensionality. The only point I'd note on this slide is that if you look at the images that are in the very bad regions like C or D, a long way from the truth, the fact that there's so many more phases across the array that are incorrect produces a very wide scattering of the power into the image. This is an example with deconvolution before the objective function is formed on the image, and here we're using a dynamic range metric. In other words, the peak intensity to some outer region RMS, and the axes and color bar are as before, but there's a substantially different structure to this solution space. If we look at its evolution, we see that it goes pretty rapidly towards the best solution in the lower left. In fact, anywhere along this left axis is fine. And the PSF correction that's been applied in this case is aiding the algorithm. It's a little more expensive, but not dramatically so. It's still well within the envelope of petascale computing. So this is a resolved source, which is why we use deconvolution. It shows a core and a jet, just a typical example. And the A and B images, the A image especially, is an excellent representation of what we would hope to find. So we've made no assumptions about the source model, and recovery is quite good. The images far away truly look bad, as would be expected. So deconvolution adds a small cost, and so it might be good to avoid that. We also looked at this type of convergence with a resolved source, but without deconvolution. Again, just looking at the encircled image in the main lobe of the PSF. And this convergence is actually quite good again, excellent again. The image lower left A is very close to the truth. Again, the PSF is not being corrected. So this is a repetition of that, except here instead of using encircled energy, we've used dynamic range. So this is an encouraging, also highly convergent solution, even with a resolved source. So I didn't want to spend too much time on those figures from our runs and blue waters. This is a slide collecting together the convergence properties. And I've shown the convergence of image objective function, the functional from the image, as a function of the iteration number for a variety of different runs, and also the phase mean squared error across the antennas in the array in the lower left. I will discuss the image at lower right in a moment. So when there's source structure or high dimensionality, as you can see in the top figure, the convergence is a little slower, but it's still quite abrupt. For comparison, this is a use of metric-free optimization in optical adaptive optics. A spatial light modulator with either 7 control channels, 19 control channels, or 127 control channels is used here. And model-free optimization is used here in a bench setting. The y-axis shows the sharpness function or the objective function, J, and it goes up and then goes down because they had difficulty setting up the spatial light modulator with random initial corrections. So instead, they just ran the optimization with opposite signs. So they degraded it and then improved it in successive cycles. So the convergence pattern is very close to what's seen in adaptive optics, which is very encouraging. If we look a little bit more closely at the regions in the solution space, this is not typically done in this object when using convex optimizers. Optimizers just the final result that people look at. So again, the x-axis here is the phase mean squared error. The y-axis is the objective function we've defined. And then the color code indicates the phase error for the antenna that's involved. And here I'm showing 8 antennas in this array. And if you look, it's pretty clear to see that the phase solution intervals, the local minima where solutions get trapped, which are not good solutions and can produce spurious symmetrized images, and other errors have distinct phase errors that get locked in and degrade the image quality there significantly. Now, this is really important because it ties into our understanding of general fidelity. It gives us an indication that we're in either a easy solution interval at the bottom where the particles can find the minimum, or a hard or impossible region where no solution is possible, I suspect, with any optimization method. But that's very important information when looking at actual data. One final diagnostic slide of the method. This shows the final iteration of one of those runs here for a point source using an encircled energy metric from the PSF main lobe without deconvolution and the optimal solution is in the lower left corner. And again, there's the banding that we see. This plot at right is decomposing the mean squared error into a pointwise antenna error and then a baseline correlation error on the y-axis. And at the beginning, iteration 1, the particle form is randomly located in the solution space, and you see this distribution here. And the colors here match the figure at left. So as the iterations proceed, the easy, correct solution gathers on the lower left. The dashed line here inside the algebra here, which I won't go into, is where the MSE is explicable only by the unknown 8 antenna phases in this particular problem. So even in the bad regions of solution space, it's still constrained by the closure relations, which is what we would expect. So in this section, I'd like to expand the discussion a little more broadly to how to assess imaging fidelity somewhat independent of the calibration or imaging estimator that is used. The estimator I've talked about up to now is designed to give us some insight into fidelity and also be a less biased method of doing image reconstruction. But what can we do when we use other traditional estimators? What does HPC enable? So in terms of understanding the fidelity per pixel, with direction dependence, in other words, we can either take real data, when we can, the smaller arrays than the square kilometer array. Simulations are a last resort, but they're only as good as the model we have of the antennas and the array. And the statistical methods is what I'm really going to talk about here. Either, again, large-scale ensemble imaging to understand the errors in the maps, or using resampling, statistical resampling to estimate fidelity. So we use that generalized data model. We have to make assumptions about the noise distribution of the errors, the thermal errors. We assume they're Gaussian, which is a reasonable assumption. And then the imaging estimators were previously described in terms of this a data model. And what we want to understand is the sampling distribution of these estimators. Right. So the simplest possible approach is, large-scale statistical imaging at scale, classical Monte Carlo method, generating an ensemble of visibility simulations for the array. Then apply the estimators directly and simply compute image statistics. So some of that work I've done on Blue Waters for SK. This is looking at amplitude errors distributed across a prototype array for the square kilometer array with either 9 antennas, 49 antennas, or 250 antennas. A very large number of antennas is possible, and the data rate goes as the square of the number of antennas. This is an amplitude calibration error that has a Gaussian distribution, and the ensemble average is about 64. So you can see there's clear direction dependence. There's no deconvolution here. And the bottom right plot shows how the RMS noise varies as antenna number. So some of the errors you often hope to simply wash out in a very large number of measurements. This is the same simulation on Blue Waters, but using here phase errors at each antenna. And as is well known to this audience, phase errors have a much more profound effect on image quality than amplitude errors. And again, we're assuming a simple point source. HPC enables new methods of statistical computing to understand the fidelity of radio images. In practice, we only have one observed visibility data set. We cannot replicate the observing conditions to generate a realistic ensemble with exactly the same atmosphere and exactly the same instrumental fluctuations. So resampling offers one way to approach this, to produce a resampled ensemble to which the calibration and imaging estimators can be applied in turn. It's a large-scale ensemble imaging problem, because of the size of the data. And then statistics can be drawn from the resampled ensemble to produce an estimate of the bias, variance, and mean squared error across the image per pixel. Generally, this is not provided by any of these heuristic iterative methods. Sometimes this will be approached through blind imaging in different teams with different methods, but this is another approach. So the fundamental underlying assumption here is the usual one in statistical resampling, that we have a data space of all potential visibilities by the array, which are governed by some very large dimensional parent PDF, which we don't know as usual. If we resample the data, we produce a resample space, B star, which in turn has the P tilde PDF. And there's a mirror relationship between those two populations and the associated distributions if asymptotic conditions hold for this particular problem. The difficulty that we have in this case is that the visibility data are not statistically independently distributed. There's long-term dependence in the data because of the fundamental nature of the of interferometry. The source structure produces a pattern in the visibility plane, a long-term trend. So the resampling has to take that into account. It has to use a resampling method that is accepting of long-term dependence. And we can then produce a sampling distribution of the point estimators from draws from that resampled visibility data space. The only challenge here is really that it's a expensive operation when interferometric image formation is concerned. So the particular example shown here, this is from some earlier work, but I mentioned it to tie it into the work I've subsequently done on good waters. The particular estimator I chose here was for a Jones matrix in that data model that captures the instrumental polarization error in each antenna. So even if you, in the interferometer, say, have a nominal circularly polarized basis, in reality, you will most certainly have elliptically polarized feed responses, somewhat elliptical. And that polarization error affects, say, the measurement of Stokes Q and U here. I'm looking here only at Stokes Q, the linear polarization. So this this generalized iterative self-calibration solution I'm plotting the mean squared error. Again, it's a simulation, so I know what the truth is. And the polarization error, the error in the Jones matrix, has not yet been fully corrected, produces a spatial distribution of error across the map. And this is the type of problem that makes interpreting interferometric images challenging. So with iteration, this generalized self-calibration reduces that residual mean squared error substantially, so the estimator is convergent and has reasonable properties. The panels that are shown at right are the bias at the first iteration and the bias at the 10th iteration, the final iteration in this particular example. Now, it's possible to estimate both the variance and the bias from the resample distribution, and I'm plotted this here to show the performance in, say, this is in variance estimation. The true variance is known from a Monte Carlo simulation, a statistical imaging simulation, and it's in the top left. Then there are 4 images. The next 4 images are a form of bootstrap resampling, where a very agnostic long-term trend is removed from each segment of the data simply as a polynomial. So it has no knowledge of the source distribution itself. And then the residuals are resampled with replacement, and the long-term trend is returned. The remaining images, the other 4 after that, use direct sort of jackknife D resampling where some delete fraction of the data are simply thrown away. And it's very clear that these methods are quite successful. The long-term trend bootstrap resampling is a pretty good estimator of the variance. And with a high enough delete fraction, the sort of generalized jackknife is also very useful. And so this gives an indication of how a calibration error translates into a direction-dependent imaging error. The bias is more difficult to estimate, as is well known from resampling studies. The true bias is in the leftmost two panels, in the leftmost panel at the bottom. The other images reflect the use of long-term dependent bootstrap resampling and the sort of jackknife D type approach. And they have some success, certainly significantly better than not attempting fidelity assessment. So I'll close up before the time runs out. We were been able to talk today about exploration of a new global stochastic calibration method that's specifically enabled by HPC and radio interferometry and is designed to address some of the scientific and engineering challenges of the current era. It's based on a very large-scale ensemble imaging approach. It produces a very promising convergence relative to model-free optimization. It's a sibling method as used in optical astronomy, but not possible there because of no direct sampling of spatial coherence. It's computationally tractable on blue waters, and there are indeed further opportunities for optimization, especially in the case where deconvolution is not used, which is why we made that separation. It intrinsically yields the structure of the calibration solution space, the antenna phases in this particular instance. So it's quite informative of bias in terms of these heuristic iterative self-calibration schemes. And it identifies regions of calibration solution space that are associated with poor quality images or images that have known defects like spurious immatization. There are interesting analogies we're pursuing with other recent large-scale parameter inference work where there's sparse estimation. It's essentially, I won't say more about it at this point, but it allows us to explain the location and nature of the regions where the solutions are either hard or impossible, and the regions where the solutions are easy or easier or can converge to the minimum. And the method in the simulations I've shown across these different parameters shows a promising robustness against source structure, which is very helpful because we don't want to impose that. The PSF quality in terms of the size and distribution of the side lobes, for example, and local minima. So it's pretty good global estimator. And it does inform our understanding of image fidelity. And I've also recapped some prior work and some more recent work on blue waters on the general problem of fidelity in interferometric imaging. It remains a grand challenge problem. Statistical imaging and resampling both provide viable methods for radio interferometric imaging fidelity assessment, and it's tractable with contemporary HPC. So this is definitely a new era. There's some new opportunities here. So thank you, Farzad. That's all I had today.
Farzad, can you unmute? Okay, thank you very much. That was great. Are there any questions they could be asked in chat? Okay, let me see. I think Farzad is muted. Let me try to unmute him.
Okay, I think it worked. Can you
All
hear
right.
me?
Yes.
Yeah.
Okay, thank you very much, Atul, for a very interesting presentation. We have a few minutes if there are questions. And if there are no questions, we thank our speaker one more time, and we can adjourn our colloquium. Thanks again.
Thank you. Thanks for inviting me.